Well, I think I guessed after I did this first slide that the title of my talk is a little bit long. So let me start by actually breaking it into pieces so that you can all know what I'm going to be talking about. So I'm going to be talking about red giants, and in particular looking at their period spacings. And what I'm really interested in is how these are affected, if they are, by glitches in the internal structure near the core. And by glitches, I mean rapid variations of their structure. Why do I want to do that? Of course, because I have hopes that it may help me identify particular phases of evolution of the stars and also give me some idea of particular regions of the cores. For those that know me, you will not expect to see any data in this talk. You will not. You will only see model results, but the hope is that I can get those that work in the data to get excited about this and look for it in the data. Of course, this is not a new thing. It has been done for other stars, and starting the sun itself, looking for the effect of the glitches on the oscillations. Sebastian just told us about that in a different application, so there's other stars to look for these things. Now, let me just start by showing you where I'm going to be looking at. So in this HR diagram that I'm showing there, I'll show you two models, which are the ones that I'm going to be presenting results. So they are examples of the kind of thing that we are doing. These are one solar mass models. My model A here is in the red giant ascent. My model B has gone through the first helium flash, but it still doesn't have the convective core. Now, we know that the oscillations in these stars, they are mixed modes, so basically they propagate into cavities, shown here, one where it's a G mode-like, and here a P mode-like, and in between you have the evanescent region where they are not propagating, but they can tunnel energy. And because I'm going to be interested in the glitches in the internal part of the star, that is to say in the G mode cavity, I show you here the buoyancy frequency, both because that's what determines the size of this cavity, and I show you here for the two models, so in red for model A and in blue for model B. And but also the buoyancy frequency determines the dynamics of the wave in this region. So what I'm interested to know really is how the spikes that you see, several of them in this buoyancy frequency, will affect the periods of the oscillations, and can we learn something from that? Before I go on, let me just point the spikes and just tell you that these result from chemical discontinuities or quasi-discontinuities. In model A here, this inner spike is related with hydrogen shell burning. The outer spike here, it results from the fact that the convective envelope went down into the region that has been processed by nuclear reactions, left a discontinuity. When it retracted back in mass, that discontinuity enters the G mode cavity. Whereas for the B case, for the B model, this spike here is again the hydrogen shell burning, and this thing here is associated one of the helium flashes. But I've said I want to know the impact of these spikes in the periods. What I'm really going to be looking into is on the period spacing, so differences in periods of consecutive modes of like degree. So what I want to see is the impact of these glitches, of these spikes, I should say at this point, in something like this. So this is the period spacing for my model A. In red, the dashed red line just shows you what the period spacing would be if these were pure G modes. So if the outer P mode cavity would not exist, then asymptotically you would expect just a constant period spacing at that value there. But because you have this coupling with the P modes, of course, you have the typical thing that the period spacing comes down at constant distances in frequency, and that is to do with the fact that you go through the frequencies that are natural frequencies in the P mode cavity, and in the modes couple and exchange energy between the two cavities more strongly, and you see this effect. So what I'm really going to be looking into is how spikes in N affect the period spacings. Now, before I go on into that, there's a very simple exercise that I think is very useful. I've been calling these things spikes, and sometimes I call them glitches. We should really see whether these are glitches or just spikes. And by glitch, I mean a structural variation that is thin compared with the wavelength. And we have to remember that G modes do have a very small wavelength in some points. So let me show you that and ask, is there a glitch or not a glitch for the case of model A? Now, here on the right-hand side panel, I show you the region of the outer glitch of model A, and here the region of the inner glitch. And superposed on that, and on an arbitrary scale, I plot an asymptotic eigenfunction corresponding to a characteristic frequency in this model, okay? And what you can see immediately is that while this guy here, which is this one here, will be seen as a glitch by the wave, so like almost a discontinuity, or at least a perturbation on the scale of the wavelength, this guy here will just be seen as a smooth transition, smooth change in the background. So I don't expect this guy here to do much as compared to what you would expect from the asymptotic analysis, a more or less homogeneous variation, a local background, while this one here might. If I go to my model B, then I'll see something similar, except that now the glitch, the spike that is a glitch, is in fact my hydrogen burning shell. Okay, so in this case, for this model, I may expect my hydrogen burning shell to have an effect in the period spacing of the kind that I'm looking for. Okay, so how do I go about to look at this? Well, I do like many people did before me in the case of studies of other glitches. I start with the simplest possible model. And that is to say, let's forget about the coupling. Coupling is too complicated, so let's focus on G modes only to start on and let the couple to later, okay? So I'll do that, and let's even keep it simple and do it analytically. So let's just assume my spike, or my glitch now, is infinitely thin, okay? So then you can do it much more easily, and you just derive this equation, which I wanted to concentrate on for just 1 minute while I explain it, in which you see the period spacing that you find when you have a glitch is just the period spacing when you don't have a glitch, which is this blue line here, the constant period spacing, the asymptotic one, over 1 plus something. Of course, when this something is small, you won't see an effect. When this something becomes significant, you may expect the period spacing to deviate from the asymptotic value. And for my model A, that is shown by the red line here, okay? And what you see is precisely that it deviates at some frequencies and goes through dips and humps. And of course, you may expect that the distance in frequency between these two dips will tell you something about the depth of the glitch as compared to the edge of the cavity, as it usually does in glitch-like analysis. And that's exactly what you see. Basically, that depends on this argument here, which is nothing less but the integral from the point of the glitch up to the edge of the cavity of n over r. So basically, it's a measure of the depth at which the glitch is. Okay, so far is the usual story. The black one is just an example to show you that if I artificially push my glitch a little bit deeper, then the change will be exactly what is expected. Basically, because it's deeper, it goes faster in frequency, the separation gets smaller, again, to show you it's a measure of the depth of the glitch. Okay, so we are still on pure G modes, but I want to go still a step forward before I include the coupling. And you've noticed, you might have noticed that these are really not infinitely thin, these glitches. And so I wanted to take into account the width of the glitch. And I could make a more complex analytical model, but the simplest thing is just to solve the equation numerically. So let's do that just considering the G modes only, so ignoring the coupling. And what I get is something like this, or what we get, I should say, because this is in collaboration with a number of people, right, is this. Now, of course, I keep that there so that I don't hide the comparison. There are two obvious differences between the two. The first of which is that there is small scale here, and the second is the amplitude dependence on frequency of this signature, which goes on the opposite way. Now, we understand this. I'm not going to be talking about these differences. They are interesting. Yeah, I may talk about them if you ask me in the corridor, but right now I want to focus on the similarity, okay? And the similarity is that you still have this shape that you expected from the effect of the glitch, which the separation is something to do with the depth at which the glitch is positioned. Okay, enough for pure G modes, right? What we want to show, what we want to look at is mixed modes, because those are the ones that couple best with the P modes are the ones that are going to be observed more easily. So that's what we want to see. So you can do that analytically and numerically, and you get a similar understanding of the problem. I'm just going to show you the numerical straight away. So this is the numerical result that you get now using adipose for the same model. So you're planning to take into account completely the coupling, and what you really want to show is this. So this shows you the period spacing for the model, which you've seen before, but now you have, this is just a zoom of it, you have over it what you get for the pure G modes. And what you will immediately notice is that whenever you have a dip in what would be the pure mode solution, you have the amplitude of this dip that is caused by the coupling with the P mode going smaller. And whenever you are on a hump, it goes deeper. And then again, a dip due to the glitch, and it goes up, and then it goes down, and then it goes up again when you reach that one. So what I want the bottom line here is that the signature of the glitch in the period spacing, considering the coupling with the P modes, is basically a change, a modulation, if you wish, of the amplitude of the dips that are caused by the coupling with the P modes, okay? Now, why is this interesting? I don't know how much of this can be observed or not, but even if you don't determine exactly the modulation, which would give you the depth of the position of the glitch, if you can somehow try to understand if there are places in evolution in which this thing is going to vary quite significantly from one dip to the other. And Dennis already showed, you might remember this from last year, KASC-7, a movie, which I'm going to show you again here, which shows that when the star goes in the along the red giant and crosses the luminosity bump, that's precisely when that glitch left by the convective region gets inside the cavity. That's where it's going to happen. So here, it's again the Brunt-Väisälä, the buoyancy frequency. The glitch is at the edge because it's still down here, the star. But as it goes up past the luminosity bump, it will get inside the cavity, and it will make something to the period spacing. So the period spacing here, what I hope you to see as this goes in, is that effect I was talking about. And then it will disappear towards here because that spike will no longer be a glitch, because then you're getting to the region where the wave is wiggling too much, and it will start seeing just as almost a slow variation of the background. So let's go for it. Okay, it's getting in. This thing, nothing much is happening. Now it's happening. You see it going on? And now it's going to disappear again because it's no longer a glitch, it's just a spike, and so forth. Okay? So basically, the bottom line here, and you can see it again, it's going again. The bottom line here is that if you could see this, if you could identify the period spacing was doing these things, you could say this star is at the luminosity bump, assuming the stars do what the models do. Okay, very quickly for this model, I only have 2 or 3 slides, so very quickly, this is just to remind you where we are. So now we're going for model B. We're looking at the hydrogen shell burning, the effect of hydrogen shell burning, which is seen as a glitch. And here is a period spacing. Now I thought to ask you whether this includes or not the coupling with the P modes. But of course it's not necessary, because anyone with an expert eye will immediately see that it does not include the coupling with the P modes. In other words, these dips have nothing to do with the coupling with P modes. Why? Well, they're not equally spaced in frequency to start with, so they cannot be. So this is what you get, the period spacing, just considering the G modes, okay? Now I'm going to overplot, changing slightly the scale, the case in which you consider the full solution, so the adipole solution in this case, which is now in black, and the G mode pure solution is in red. What you see here now is the effect of the coupling with the P modes, equally spaced in frequency, as it should, right? But in between, you have a number of dips in the period spacing, almost as deep as the other ones, which are, well, these are basically G modes. You see there's a almost perfect overlap between the two curves. So these are not the result of coupling with anything. What is this? Well, this is just what I was talking about. This is just the effect of the glitch. It gets a little bit more interesting even. Actually, I wanted to, well, I can say it in this plot. The interesting thing here is that if you could see them, and you could see this separation, then you could have a measure of the depth of the hydrogen burning shell. Now, can we see them? I don't know the answer to that. I hope you that work with the data will be able to tell me. But the thing is, when you look at the normalized inertia for these modes, you see that basically you see the minimums. This is for the L equals 1, this is the L equals 0 just as a reference. The minimums in inertia associated with the coupling with the P modes, as we always do. These are the most observable ones, the easiest to observe. But then you see local minima around these modes that have nothing to do with coupling with the P modes. What is happening here? Well, most of you have, I'm sure, have guessed what's happening. What's happening and is shown here, I picked two frequencies, two modes, one at the maximum, local maximum, the other at the local minimum. They are not coupled with the P modes, almost not. I mean, really, they're always a little bit, of course, but not, they are pretty much G modes. And here are the eigenfunctions. Now, this position here is the position of the hydrogen burning shell. So what's happening is simply that this guy here is trapped or partially trapped inside in the inner part of the cavity, while this one here, if transition goes up, it's more trapped in the outside cavity. Hence, their inertia is smaller, and perhaps they'll be more observable. Again, if you can observe this pattern, you'll be able to determine the depth of in a measure of the depth of the hydrogen burning shell. So that brings me to my conclusions. Just a warning. The first one is that some spikes in the Brunt are glitches and can have an effect, others not. It really depends. Don't forget that G modes oscillate a lot, and so a spike is not necessarily a very sharp phenomenon as seen by the glitch. And then we understand the signatures of these spikes in models. We don't know if our models represent well the reality. And if they are found in space-based data, then you may be looking at identifying specific phases of evolution and also measure positions of specific regions, in this case that I've shown the position of the hydrogen burning shell. Thank you very much.
JJ?
So in all your plots, you show these as continuous distributions, but of course they're discrete in the stars.
Yeah, of course. I meant to say that.
And I wonder what's the lowest radial order you think you could get away with? I'm wondering if like an L equals 3 or L equals 4 set of modes, if we could see them at high enough amplitude, you could actually get the resolution to actually try to do this observationally.
You're talking in terms of the radial order, or are you talking about?
In the spacing and frequency, to actually start to resolve these dips. It doesn't
the
seem like you could do it
spectrum,
with an L equals 1.
The spectrum in this case, these are L equals 1 modes only, right? I'm just showing L equals 1 mode, but the thing is that the spectrum is extremely dense. What actually, if I go back to one of these slides from my period spacing, for instance, you'll see I'm connecting the positions of each pair of modes. But the fact that it's a smooth curve shows you that it's extremely dense because these are G modes. So you have.
Oh, so this is discrete already.
Sorry?
These are the discrete.
Well, they are not discrete. They are. I'm plotting them as line. But the fact that it's smooth shows you. Actually, you can see that in the inertia. So you can see the number of individual modes you have if you look at the inertia, right? Good. So there, each of these crosses is a mode, right? So it's very dense.
So you could do it with L equals 1.
Maybe. If we can observe them. The question is whether you can observe these that are not coupled with the P modes, because usually you observed mostly around those. But the observers will tell me. I mean.
Cool.
Jan and Mark?
So just to be clear, your model B is just after the helium flash and before the star settles down.
Yes, it doesn't have a convection.
So it's a very short phase of evolution, and so we have to really look a bit at statistics of how the star, because it's also a phase where there are intermediate flashes and convective shells where the spectrum becomes even more complex.
Sure. No.
But of course, it's very, very, very interesting and very promising. In this case, you can actually see this kind of signal.
Yeah, if I may add something to that. I mean, of course, all along this path until you get a stable helium, the helium core burning, the convective core, you have a number of, the cavities are changing very strangely, going from one cavity to two cavities, like other people have shown before. And so I'm showing this particular model, but we expect that in that fast phase, probably all the models will show something weird, and we are analyzing other models along that phase to see how it changes and what kind of trapping you may find. But also, of course, we should analyze the more evolved models, slightly older with a convective core, to see. This is just examples of, because we are trying to cover the whole thing and do a systematic search. Actually, Dennis is doing a systematic search for these kind of things, covering the whole evolution.
Right.
Thanks.
One of the most interesting, I think, true discontinuities you expect in a red giant branch model is at the first dredge up, when you basically form a sharp basically feature in hydrogen. And This would show up only on the lower red giant branch, where basically you've dredged up the partially hydrogen-burning products, and I have no feel for whether there's any seismic detectability of that, but it would be extremely interesting if possible. Yeah, right. That's precisely what. Yeah.
It's a luminosity bump.
No, not talking about the luminosity bump. I'm
You
talking
see,
about before.
you say.
On the lower giant branch when you develop
okay.
the first dredge up, not the bump, right?
I think Dennis wants to respond to that.
So the feature that Margarida showed that was at the higher radius is from the first dredge up.
Okay.
Yeah.
So that is what you're.
Exactly.
Because I think of that as being at the very low luminosities.
No.
It's still low. If you look,
it happens very close to the bump.
Okay.
Yeah.
So the first dredge up only starts to retract just before the bump.
Okay.
And that is where the feature, in the model at least, also start to interact with the modes in terms of their wavelength.
Because the thing is that you're going deeper and deeper, right, to the convective envelope, and then while you're going deeper and deeper, the glitch is at the edge of the G-mode cavity, of course, but it's only when you start retreating, which is about that time, when you start retreating, it goes inside. Yeah, it retreats in mass, and so the glitch goes inside the cavity. That's why it's a very precise moment in evolution. Yeah.
Mine's a very simple question.
Yeah, sorry.
Just to add a brief mea culpa to this discussion, that in the Aztec models there is some numerical diffusion which makes this, what really should be a discontinuity in composition, slightly smoothed out. And that's why the glitch doesn't look quite as sharp as it probably, or possibly, or whatever should. But
your analysis was using the Cowling approximation.
Yes, it was, yeah.
But the subsequent results were from full calculations.
The mid-part results were in the Cowling approximation. The analytical analysis were in the Cowling approximation. The first numerical analysis, so that first pure G-mode cavity, this one is in the Cowling approximation, is solving the same second-order differential equation, but numerically. And then this one, and this one, is full.
So my question is, does
sorry.
analytic solution,
Sorry?
does the analytic solution that you showed match the detailed numerical solutions? i.e., is the Cowling approximation valid?
Yeah, well, I've not checked that. Well, actually, I've checked. No, I've not checked that. I've checked the solution, the numerical solution in the Cowling approximation with the with the analytical solution in the Cowling approximation. No, I have not.
All right, let's thank Margarida again.